Hello, I'm Gerald, and I'm going to be solving this question from the homework tool. It's about process memory and it's the In-DRAM bitmap index 2 question. So the question statement says that you're going to design a database from Etihad and you profile the system and then you figure out that one of the most executed queries is this one, selected the hometown of students. They are from Switzerland and speaks German. And also figure out that the database have three attributes: hometown, country, and language, and are encoded using a 4-byte binary representation. So the database size is 32K elements, and each attribute is stored contiguously in memory. So the database executes the following query, as it said. It checks if the student is from Switzerland, and if the language is German, and then if it's true, it's assigned it to true to the position hometown array, and if it's false, assign false to the position hometown array. So in the first part of the question, it says that you're going to run the above code on a single core processor, right? And there are many assumptions about this processor. It has a 8 megabytes directed map cache with a cache line of 64 bytes. And a hit in this cache takes 1 cycle, and a miss in this cache takes 100 cycles for both load and store operations. So all load and store operations are serialized, and here I have the start addresses of the arrays that store the entries of the database. So we have this address here, the other one, and the other one. And the execution time of non-memory instructions is 0. So it asks how many cycles are required to run this query. So since the execution time of the non-memory instructions is 0, the number of cycles is going to be given pretty much, but the number of access that you do to the cache, so the number of hits in the cache, number of hits in the cache times the hit latency, which is 1 cycle, plus the number of misses times 100 cycles. And now you need to figure out the number of hits and the number of misses in this cache, right? So the question says that you have a directed map cache of 8 megabytes and the cache line is 64, right? So you need to figure out if those addresses are going to hit or miss in the cache. So we have the cache address here, the line address, and it's 32 bits. And then you're going to split this into the offset of the cache, the index, and the tag, right? And then you need to figure out when is the offset, where is the offset, the index, and the tag. So the first thing is the offset. So the cache line is 64 bytes. So this means that you need 2 to the 6 bits. So you have to the offset from bits 0 until 5, those 5 bits, right? Those 6 bits. And then you need to know how many cache lines you have in this cache. So number of cache lines is going to be equal to the cache size, which is 8 megabytes, so 2 to the 23, divided by the cache line size, 2 to the 6, and then this is going to be 2 to the 17. So you need 17 bits for the index bits, so this is going to go from 6 until 22. Then 23 to 31 is the tag, right? Okay, now we need to figure out what is going to happen when you access the cache, right? So pretty much we're going to do a load operation first for the address 0, 5, 0, 0, 0, 0, 0, 0, and those numbers are in hexadecimal, and then another load for address 0, 0, 6, 0, 0, and then 0, 0, 0, 0, and then the other one is going to be a store for address 070, this one. So, okay, so we have the first address here, right? So those first parts here is going to be 000, so from bits 0 until bits 15 is going to be all zeros, right? And now we need to figure out bit 16 is going to be 0, 17 is going to be 0, 4 zeros, then more 4 zeros, then 5, then 0, 0, whatever, right? And then, so we need to figure out bit 6 until bit 22. So this is 16, 17, 16. This one is 22. I'm not wrong. So from bits 0 until, from bits 22 until bit 6, let's say someone here, your index is always going to be 0, right? And for the first address here. But if you change to the next one, the zeros here are going to be all the same. What is going to change is this number over here, right? I have a 0 more. This is 5. This 5 is going to change to 6, right? And the other one is going to change to 7. But the rest here is always the same. It's all zeros and zeros. So what does it mean? It means that every time that you do a memory access here, you're going to have a cache conflict, and then it's going to have a miss. So throughout the whole execution of these operations is going to be all of those load and store operations are going to miss in the cache. So the number of hits is going to be 0. It takes 1 cycle. And the number of misses is going to be, you're going to do 3 times memory access, right? 2 loads and 1 store. And the number of elements that you have is the number of entries in your database, 2 to the 15. And times the latency, which is 100 cycles. So this is the number of cycles that you're going to take for you to execute this operation. Okay, so the next part now, it's about, the next part now is about, it's about ambits. So it says here that we discussed ambit, which is the RAM design that can greatly accelerate book bitwise operations that have the ability to execute AND, OR, and XOR of 2 rows in a subarray. So it's saying that ambit works by issue back-to-back activate and precharge operations. And it gives an example here how it works for AND, OR, and XOR operations, right? And it also says that ambits have some rows, like some control rows that detects if you're going to execute an AND or an OR operation. And some rows, there are these duality context cells that are used for perform bitwise NOT operations on the data. And here are some assumptions about the memory device that is going to be used to execute ambit operations. So you have that the DRAM row size is 8 kilobytes. The activate command takes 50 cycles to execute. A precharge command takes 20 cycles to execute. The DRAM has a single bank. The syntax of an AMD operation is BBOP, and then you can decide if it's an AND or XOR operation. You have the destination array, this first one and this first 2, and then you have the addresses of some arrays, some rows in the subarray that are used to store partial results. And then you have the row addresses that store the constants that you're going to compare with. So Switzerland or German over here. And also it says that in each of those elements is stored in 4 bytes throughout the entire row. So over here we have some of the sequence of AAPs that are used to do ambit and operation or XOR operation, right? So, and then the question starts. The following code aims to execute the query that you are trying to accelerate before. Selected the hometown of students that are from Switzerland and speak German in terms of Boolean operations to make sure to use ambit. So it asks you to fill the boxes such that the algorithm produces the correct result and show you, right? So there are 4 boxes here. The first one to ask is for how long this loop is going to execute. And then is the sequence of Boolean operations that ambit is going to execute, right? So let's do the first thing first. How many times this loop is going to execute, right? So you have a DRAM row that is 8 kilobytes, right? which is 2 to the 13. And you are going to store each element, you're going to encode in four bytes. So the encoding is 4 bytes. So it means that you're going to have 2 to the 13 divided by 2 to the 2, which is 2 to the 11 elements inside a row. So now the question is how many times or how many rows you're going to have to store all of the computation. So you have that the database size is 2 to the 32K, so it's 2 to the 15. And one single row stores 2 to the 11 elements, right? So this is going to give you 2 to the 4, which is 16. So you need to repeat this loop 16 times. Now we need to figure out what is the sequence of operations that you're going to generate the instruction, right? So the sequence of PPO operations, right? So let's do some thinking over here. So pretty much, let's say that you have, let's say that you just have two languages. So let's say in the database, you have, I don't know, German and Italian. And the student can come from Switzerland, or it can come to Italy. Let's say, okay. So what we want? We want, let's see, the truth table of this. So the student can be from German, can be from Switzerland, let's just say CH, and can speak Italian, or the student can, this is the country, and the language over here. The student can speak German, let's say German, or Italian, right? Italian, German, Italian. So in the first query, let's say this is your database, right? And then you have 3 queries. The first one is you want to figure out if the student comes from Switzerland. So you are going to want this line over here, this line over here. This is Italian. You don't want this one. You don't want this one. The second one asks if you want the student that speaks German. So you want this line here, you don't want this line here, you want this line here, you don't want this line here, right? And in the end, you want both. You want the student to come from Switzerland and speak German. So the only line that's important for you is this one. And then you don't want this one, you don't want this one, you don't want this one. So the first query that you're going to execute is going to be this one over here, right? Is with the country. And then you're going to have your database with CH, Italy, and your query is pretty much CH, right? CH. You want the person to come from Switzerland. And the result, as we saw here, is we want this line, we want this line, we don't want this line, we don't want this line. So when you look at the database, you see that the lines that you want is the lines which both elements here are equal, right? So this one is equal to this one, this one is equal to this one is different, so you don't want it, this one is different, so you don't want, right? So which Boolean operation can give you this? The Boolean operation that can give you this is XNOR, right? So the truth table of XOR is 0, 0, 1, 1, 0, 1, 0, 1, the opposite of XOR. And this gives you 1, 0, 0, 1. This is exactly what we have over here, right? let's see for the next operation. So for the next operation, we have the language, and you have German, Italian, and you have German, Italian. And what you want is pretty much German, right? So you want to run this against German, it's a query German, 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 German. And you want this line, you want this line, you don't want this line, you don't want this line. And if you look here, these two equal to each other, these two equal to each other, right? So the same operation works, XNOR. However, that is something, right? In the operation that we provide over here is either AND, or XOR, right? You could do a XOR operation and then you could negate this operation over here. But if you look at the sequence of instructions that are here, is only 3 BBOPs, right? There is no BBOP not of the result. And so how can we encode this? So the trick in this question, it's pretty much that we are not trying to say that the results, you're not trying to say that truth is equal to 1 and false is equal to 0, right? If you assume that truth, element is true, is going to be encoded with 0, and false is going to be encoded with 1, and then let's say that you have here 0, 1, and like Switzerland is encoded with 0, and Italy is encoded with with 1. Here is wrong. So 0, 0, oops, 0, 1, 1, and then this is going to be 0, 0, 0, 0, right? So if I do XOR instead of XNOR, I'm going to have that 0, 0 is going to be equal to 0, 0, 0 is going to be equal to 0, 1, 0 is going to be equal to 1, 1, 1, 0 is going to be equal to 1. And same thing here. Let's say that German is equal to 0, Italian is equal to 1, so this is going to be 0, 0, 1, 0, 1. This is going to be 0, 0, 0, 0. And then this is going to give you 0. This is going to give you 1 if you do an XOR operation, right? Instead of XNOR. And then you're going to have 0 here. Then you're going to have 1, right? So again, our encoding means that 0 is equal to true, 1 is equal to false. So what was selected was exactly the line that you want, right? This is true, this is true, this is true, and this is true. So, okay, so the first operation that you have here is a XOR, then you have a XOR, and then the other operation here that we're going to have in the end is that you want to select 1. So in the end, you're going to have here 0, 0, oops, 0, 0, 1, 1. This comes directly from here. And this, we're going to have 0, 1, 0, 1. And this comes from here. So, okay. We want to select only the first line, right? So let's say if you do an AND operation, you're going to have 1 in this line, you're going to have 0 in this line, you're going to have 0 in this line, and 0 in this line, right? So 0 is true, and you have many trues, 1 not true, so you don't want this, right? You just want to select the first line. If you do a XOR, it's going to have that this is going to be equal to 0, this is going to be equal to 1, this is going to be equal to 1, this is going to be equal to 0. Again, you select the two lines, you just want the first line. So this is not the operation that you want. But if you do a OR operation, it's going to be 0 or 0, 0, it's going to be 1, 1, 1. Again, true is equal to 0, so you just selected the line that you want, the first one. So 0. So the other operation that you need is going to be a OR operation. Okay. So this was the second part of the question, right? And then finally, the question asks you how much speed up does Ambit provide over the baseline when executing the query. So pretty much what we need to understand, what we need to do is figure out the time to execute Ambit operations. So you're going to execute this loop here 16 times, right? And in this loop, you have 2 times XOR operation and OR operation. And the ANDs have 2 times 2 times, okay. The latest that is going to take, or the number of operations that you're going to take to execute an XOR is how many APs and APs, right? This is what determines the latency. So here you have 1, 2, 3, 25 AP plus 11 is plus for the OR is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 APs plus 11 A's, 5 B's. So the time is going to be 16, 2 times 25. The time for A is equal to A 50 cycles plus the time of a P is 20 cycles plus 50 times 11 plus 5 times 3. Okay, so the speed up is going to be the time that it takes to execute on the CPU divided by the time that it takes to execute on Ambit. The time to execute on the CPU we figure out in the prior question is 3 times 2 to the 15 times 100 cycles. And for Ambit is what we just had over here, is this latency over here. So this is going to give you the speed up. So it's pretty much this. Hope it's clear how to solve the question. The key is to have this assumption over here. And pretty much that's all. So good luck with the exam. And
I'm going to discuss a set of the questions we covered in homework 4. Basically, the questions are about non-volatile memory technology. Let's see the question. A researcher has developed a new type of non-volatile memory, BossMem. He is considering BossMem as a replacement for DRAM. BossMem is 10 times faster. All memory timings are 10 times faster than DRAM. But since BossMem is so fast, it has to frequently power off to cool down. Overheating is only a function of time, not a function of activity. An idle stick of BossMem has to power off just as frequently as an active stick. When powered off, BossMem retains its data, but cannot service requests. Both DRAM and BossMem are banked and otherwise architecturally similar. To the researcher's dismay, he finds that a system with 1 GB of DRAM performs considerably better than the same system with 1 GB of BossMem. And the first question is, what can the researcher changing or improve in the core? He can't change BossMem or anything beyond the memory controller. That will make his BossMem perform more favorably compared to DRAM. realizing that he will have to be fair and evaluate the DRAM with his enhanced core as well, 15 words or less. So this question limits the number of words in the answer, so which is asking for explaining only the core idea very briefly. Basically, the main drawback of BossMem is the periodic power off. For the same amount of time, it can operate. So overheating is only the function of time, not a function of activity. Okay. So let's see how it affects the system performance with an extreme example. So BossMem alternates two phases. So this is timeline. And the first phase is power off, power on. And the other is power off. And BossMem alternates these two again and again. Suppose that the system issues two memory requests, A and B, at the beginning of each phase, respectively. So in this case, request A can be quickly handled, but B needs to wait until the end of power off phase, which leads the system to be stalled for the same amount of time. So a possible way to mitigate this penalty is to perform the memory access to B in advance when it becomes necessary, so that the system can provide the data, use the data B when it becomes necessary without accessing the BossMem, which should be powered off. Okay, so the possible answer should be prefetching or other speculation techniques like value prediction or out of order scheduling that enable caching of data which is necessary during BossMem's power off phase. Okay. Let's see the next question. A colleague proposes he builds a hybrid memory system with both DRAM and BossMem. He decides to place data that exhibits low raw buffer locality in DRAM and data that exhibits high raw buffer locality in BossMem. Assume 50% of requests are raw buffer hits. Is this a good or bad idea? Show your work. Okay, basically, when we make a decision with such heterogeneous devices, we should consider the benefit or cost of the decision. Then, what is the benefit of allocating data with high raw buffer locality to each memory? It is that we can avoid raw miss penalties, which is for fetching the requested data from memory cells to the raw buffer, right? So let's consider the raw miss penalty in DRAM. When the request hit the raw buffer, let T hit be the latency for the low hit request. And for raw miss request, the latency will increase due to pre-charge and activation. So T miss should be T hit plus alpha for the other operation, so the pre-charging and activation. And alpha is typically larger than T hit, right? So this is DRAM. And when it comes to BossMem, as explained in the question, BossMem is architecturally similar to DRAM. So its raw heat latency should be also comparable to T hit, right? On the other hand, as its timing parameter is 10 times shorter than those of DRAM, its raw miss penalty, which is alpha, should be also 10% of that of DRAM, right? So if we consider only the benefit of storing high locality data in each memory, the BossMem's benefit is only 10% of DRAM, that of DRAM, right? And also, during the power-off phase of BossMem, we cannot benefit at all from storing high locality data in BossMem, right? So the possible answer should be no, it's a bad idea because the first reason is, so DRAM's raw miss penalty is more significant and BossMem cannot benefit at all from high locality data when powered off. Okay. So question 3. Now our colleague suggests trying to improve the last level cache replacement policy in the system with the hybrid memory system. Like before, he wants to improve the performance of this system relative to one that uses just DRAM, and he will have to be fair in his evaluation. Can he design a cache replacement policy that makes this hybrid memory system look more favorable? In 15 words or less, justify no or describe a cache replacement policy that would improve the performance of the hybrid memory system more than it would DRAM. Okay. So, okay. I think it is yes. It should be yes, as long as we design the system properly. So again, this question this question is also asking for just explaining the data, the idea very briefly, using only less than 15 words. Okay. So the main drawback of BossMem is purely power-off, and we can mitigate the penalty by avoiding accesses to BossMem during the power-off phase as much as possible. So how can you do that in cache with the cache replacement policy? One possible solution is that prevent addition of data which is allocated to BossMem while the BossMem is powered off. So a possible answer is yes. And the cache replacement policy should select a victim considering the data allocation meaning where the victim is stored currently, and the BossMem's power on or off status, right? Okay. And next question is, in class, we talked about another non-volatile memory technology, phase changing memory, or PCM. So question is, which technology, PCM, BossMem, or DRAM, requires the greatest attention to security? What is the vulnerability? Okay, and the next question is, which is likely of least concern to a security researcher? So the questions are asking about the security properties of each memory technology. So let's first think about potential vulnerabilities of each memory covered in this class, in our class. Okay, first, PCM. It has a serious vulnerability actually due to its non-volatility, which is commonly called data remanence problem. Meaning that after the power off, an adversary can obtain stored data in some memory. And in fact, the system, the normal system can protect the stored data in memory from the malicious access by with the OS protection like permission checking, right? But once it is powered off, an adversary can detach the memory module itself and can directly access the memory via custom memory controller. And then, if the memory device if the memory device still retains the data, then the adversary can easily obtain the confidential or private data stored in the memory device. And we call this problem as data remanence problem. And also PCM, as we have learned, it has a limited endurance, right? Endurance. It can only endure only for a certain amount of program operations. So an adversary can quickly exhaust the lifetime of a PCM chip by maliciously issuing requests very intensively, write requests very intensively to the chip, which is commonly called endurance attack. So these are what I can think of as PCM's security vulnerability. But in DRAM, sure, DRAM is relatively free from these security concerns, as it is fundamentally volatile memory and virtually has no endurance limitation, right? But yeah, it has another a different, perhaps more serious security vulnerability, as we have learned, which is a RowHammer, right? So there is a work that demonstrates that an adversary can obtain the system's root privilege, which is quite serious situation, without directly accessing the system, meaning remotely accessing them. And how about BossMem? As this question does not assume any limitation in BossMem's endurance or something like a RowHammer effect. So it has only data remnants problem, as it is also non-volatile memory. So according to this analysis, I think we can say that PCM is more vulnerable compared to BossMem. I think it is what we can, it is only thing what it can say. But it is quite difficult to clearly say, for example, when you compare PCM and DRAM, I think it is quite difficult to clearly say one is more vulnerable than the other, as they have different security vulnerabilities, and people actually can think different way in what is the most serious security vulnerabilities, right? So basically these question 4 and 5 are open-ended questions. So you would get full credit if you reasonably explain your thoughts based on something like this analysis, security vulnerability of each memory technology.
Okay, I'm going to solve question 6 in homework 5. And the question says the following. We have a system with 4-byte addressable processors. Each processor has a private 256-byte Bitmap write-back L1 cache with a block size of 64 bytes. Coherence is maintained using the Illinois protocol or the Messi protocol, which sends an invalidation to other processors on writes, and the other processors invalidate the block in their caches if the block is present. As a note, on a write hit in one cache, a cache block in shared state becomes modified in that cache. Accessible memory addresses range from this address to this other address. From this to this. Assume that the offset within a cache block is 0 for all memory requests. We use a Snoopy protocol with a share bus. So, cosmic rays strike the messy state storage in your coherence modules, causing the state of a single cache line to instantaneously change to another state. This change causes an inconsistent state in the system. We show below the initial tag store state of the 4 caches after the inconsistent state is induced. So this is the initial state, and the question is, what is the inconsistency in the above initial state? Explain with reasoning. So, okay, we can solve this question by looking at the modified and exclusive states, these modified and exclusive states. So if a cache line is modified or exclusive state in one cache, this means that it cannot be present in another caches. So we can start checking these states. Okay, let's start with this cache line that has an address with this tag and with this set. And we can check that it's not present here. In cache 1 is not present in cache 2, and is not present in cache 3. So this should be okay. So let's check the next cache line that is in exclusive state. So this is in cache 0. We can see that it's not in cache 1. We can see that it's not in cache 2. And we can see that it's not in cache 3. So this is okay as well. So no more modified or exclusive states in cache 0. So let's move to cache 1. Here there is no modified or exclusive state. Let's move to cache 2. So okay, let's check this cache line. This cache line, let's check if it's in cache 0. It's not in cache 0. It's not in cache 1. and is not in cache 3. So this should be okay. This cache line is in an okay state. Let's check the next one, that is the set 1 in cache 2. Let's do the same. So in cache 0, we can see that it's not in cache 0 set 1. It's not in cache 1 set 1. But it is in set 1 cache 3. So basically it's here as well, and we can see it's exactly the same cache line, but it's in shared state. And we can see that these two states for the same cache line in different caches are inconsistent. So we cannot have the same cache line in exclusive state in one cache and in shared state in another cache. So we detect the error here, right? This is the error. And the possible error here is that, so the initial state before the strike, the cosmic ray strike, could be that this could be in invalid state, and then this exclusive state here could be valid. Or let's clean this up a little bit. So this could be invalid state, or this could be in shared state. So we have two lines in shared state. So okay, we detect our error here. Let's go to the next question. The next question says the same, the following. Consider that after the initial state, there are several paths that the program can follow that access different memory instructions. In B1 and B2, we will examine whether the following path can potentially lead to incorrect execution or an incorrect result. So the question is, could the following path potentially lead to incorrect execution? Explain. So let's analyze this code. So let's start for the first instruction. First instruction is execute in processor 2. And this basically, so first we have our tag that is for 24 bits, as we can see here. So we have 3 bytes for representing the tag. And because we have 4 sets, we need 2 bits to represent the set, right? So we have 24 bits for the tag, and 2 bits for the set. So this means that this address here is a 4. And also we assume at the beginning that the offset is always 0, right? So if we see this this byte here that contains the tag, this byte contains the tag, we have a 4. This is basically 1, 0, 0, 0, and these 2 first bits are the bits for that represent the set. So basically we are in set 1 here. Okay, let's check. So set 1, and we are accessing in processor 2. So basically we are accessing one of we're accessing the cache line that is affected by the cosmic rays, right? So we are reading this line here that is in exclusive state. And we mentioned before that the initial state could be exclusive or shared. So by reading this data, is not any problem at all, right? Because it wouldn't change if it's in exclusive or shared state. The data should be the same. So executing this instruction should be okay. And the next instruction, this doesn't affect to the cache line that was struck by the cosmic rays. Then the next instruction is this one in processor 3. That is again the line that was affected by the cosmic ray. And at this point, we store in this line, right? That remember initially could be in shared or in invalid state, but because we are writing in it, basically we are changing the state from shared or invalid to modified, and we are writing the data, so there is no inconsistency there. And because we are writing, we also invalidate the other copies in cache 2. So there is no problem there, because we will be writing here, we will be writing in cache 2, in cache 3, sorry. We will be writing cache 3, we will change the message state to modified, and we will invalidate other copies. So there is no problem there. It should be okay. This should be okay. The other instruction and the next instruction doesn't affect to the cache line that was struck by the cosmic rays. The next instruction is actually loading the cache line that was struck by the cosmic rays, but because now we are in a consistent state, because we store and we invalidate the other copies, now our cache is in consistent state. So now we are reading. Now we are reading here, and everything should be okay, because the cache state is consistent now. And in the last instruction, yes, it's an address that is not a polemic address. It's not a conflicting address. So, answering this question, could the following path potentially lead to incorrect execution? And the answer is no, because after this store, the state of the cache becomes coherent and consistent. So let's go to the following question. Could the following path potentially lead to incorrect execution? Explain. So let's do the same. So let's start for the first instruction, that is executing processor 3, and is the instruction that was struck, is the cache line that was struck by the cosmic rays. Yeah, is in the set 1, and is the tag that is basically this instruction at the beginning. So basically we are loading. Let's go at the beginning. Maybe it's easy to see here. So basically you are loading this address. What's the problem with this? Yes, we are loading this. That if you remember from the first question, this actually could be in shared or invalid state. If the case was that the initial state before the strike was invalid, we will be reading invalid data here. Okay, so the answer to this question is, could the following path potentially lead to incorrect execution? The answer is yes, because we could be reading some invalid data here. Okay, let's go to the next question. After some time executing a particular path, which could be a path different from the paths in the previous parts, and with no further state changes caused by cosmic rays, we find that the final state of the caches is as follows, and we see the final state here. The question is, what is the minimum set of memory instructions that leads the system from the initial state to the final state? Indicate the set of instructions in order and clearly specify the access type, load or store, the address of each memory request, and the processor from which the request is generated. So, okay, we have the final state, and here on the right, we have the initial state. Let's check the differences. So in cache 0, the difference is that in the set 3, previously we have an invalid state, now we have a valid state for the same cache line. For cache 1, we have in set 0, previously we have another tag, stack, and in set 3, previously we have a shared state. In cache 2, previously we have a shared state in set 3 and the same tags in sets. In cache 3, previously we have exclusive state in set 0. And I think that those are all the differences. So we have these differences, okay? Okay, so let's see what we can do. So we can see that in cache 1 and cache 2, we have two cache lines. Actually, it's the same cache line that is in shared state, and we need to invalidate. For invalidating that, what we can do is use the processor 0, because we already have to modify the set 3 anyway. Like in cache 3, we don't need to modify the set 3. So let's use cache 0. To invalidate set 3 in caches 1 and 2, we have to store the same cache line that is in cache 1 and cache 2 in set 3. So we store the same address. We have to specify the set as well. So the sets are 2 bits. So we have, if we are in set 3, we have 1, 1, and because we assume that the offset is 0, so we have 1, 1, 0, 0, and this is C. So we need to put a C here, and the rest of the offset is 0 as well. So with this first instruction, we have in the final state already the cache 1 set 3 and the cache 2 set 3. Okay. To set cache 0 in the final state, we need basically to load this address again. And by loading this address again, we will put it automatically in exclusive state because this address is not present in any of the other caches. So we just load 0, 5, F, 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 F. This is in set 3. Okay, so we have cache, the set 3 of cache 0 already in the final state. Let's go to cache 1. So we see that we have to load in cache 1 this address because before was a different address, a different tag. And we can observe that the final tag is the same as the set 0 in cache 3. But the difference is that the final state in cache 1 is invalid and the final state in cache 3 is modified. So basically, we need to load the line in cache 1 first so we can invalidate it from cache 3. So let's do that. So we have cache 1. we load our cache line FF000. This is in set 0, so set 0 and offset 0. So by doing that, we load this cache line in cache 1 in S state, actually, and we put this in S state too, in cache 3. So the final step, we need one more instruction to put this cache line, modify the state in cache 3, and invalidate the same line in cache 1. So let's do that. In cache 3, just store our cache line 000 in set 0, offset 0. And doing this, we go to modify the state in cache 3 and to invalidate the state in cache 1. So that is the solution for this question.
Hi everyone, so I'm going to explain to you the exercise from homework 5, which is Runahead Execution. So to make clear, like there is a mistake in the exercise, in the question. So the loop for in the code doesn't start from 12, it starts from 0. So we'll send an email regarding that. So let's see the questions in the exercise. So first we assume an in-order processor that employs Runahead Execution. So we have an in-order processor. The processor enters Runahead mode when there is a cache miss. So whenever we have a hash miss, we will enter Runahead mode. And there is no performance penalty for entering and leaving the Runahead mode. There is a 64 kilobyte cache and the cache block size is 64 bytes. The instructions are fetched from a separate dedicated memory that has 0 access latency. So we don't take into account any instructions. The cache is 4-way set associative and uses the LRU replacement policy. And the memory request that hits in the cache is serviced instantaneously. A cache miss is serviced from the main memory after X cycles. We're going to discover more about this X. A cache block for the corresponding fetch is allocated immediately when a cache miss happens. The cache replacement policy does not evict the cache block that triggered entry into Runahead until after the Runahead mode exited. This means the following. So if we activate Runahead and we bring one cache block into the cache, and this cache block is the one responsible for the entering Runahead, you cannot evict it from the cache. So imagine activating Runahead for this data, for this piece of data. So if you bring this piece of data into the cache, you cannot evict it until you exit Runahead. So a prefetched block from Runahead cannot evict this data block. So the victim for cache eviction is picked up at the same time as a cache miss occurs. Okay, this is critical. So ALU instructions and branch instructions take one cycle. That's important. And the pipeline does not stall for any other reasons rather than data cache misses. So consider the following program. So in this program, we iterate 100 times over some computation, and we need to load this memory location A. And we have here some like offset, which is 16 multiplied by 1024. And as you can imagine, like if you multiply by 16 multiplied by 1024 for different i's, then you end up having the memory location, each cache block location goes to the same set in the cache. Okay, so what's the first question? After running this program using the processor specified above, you can find that there are 66 data cache hits. And what are all the possible values of the cache miss latency X? So and you can specify them using an inequality and show your work. Okay, so how many memory accesses do we have in total? We have 100 memory accesses, right? Okay, so with 100 memory accesses, we want 66 hits. So we need, how many misses? We need 24 misses. No, sorry, not 24, 34. 34 misses. Okay, for 34 misses, what do we want? We want 34 misses, and for every miss, we need to prefetch 2 things. So if we prefetch 2 things, we will end up having prefetched 68 cache blocks. So and this can lead to the 66 hits. So for every miss, we will prefetch 2 times, which means that whenever a run ahead prefetches, it will prefetch 2 blocks ahead. So another issue is that like after we have a cache miss, and to reach the next load instruction, so the processor needs to execute one ALU instruction for the +1. It needs to execute, so it's 1 ALU. It needs to execute 26 ALU instructions here, as it says in the program, plus 2 ALU, as it says here, and one branch, and all these take 1 cycle. So to be able to reach a load instruction 2 times in run ahead mode, you need to execute at least it's 1, 2, 3, 31. Yes, 31 instructions, and 32 if we want to execute, and 62 if we want to execute 2 loads. So the processor needs to have at least 62 cycles, so the initial memory latency of the cache miss that triggered run ahead needs to have at least 62 cycles to be serviced, so that run ahead mode has time to go in and prefetch. So imagine that we had the miss here, and this is the run ahead, and here we're waiting for the miss, and we know that the miss will come 62 cycles after that. So here run ahead will be able to go and bring the first cache block and the second cache block, the ones that we need, because we need 2, and then it will exit after the 62 cycles of the miss. But the problem is the following. So we need to find the upper bound of the inequality right now. So if run ahead, if the miss is served after 92 cycles, which means that here we won't spend 62 to execute 2 loads, but run ahead will spend 92 and it will execute 3 loads, 3 prefetches. Then it will prefetch 3 blocks. If it prefetches 3 blocks, then this will not be 66 hits, it will be a different number. So the number for the total latency will be between 61 and 93. I will repeat. We need for a miss, if the miss lasts 62 cycles, then run ahead will have time to go in, fetch the first prefetched block. It will execute 31 instructions to reach the second memory miss, and then another 31, and it will go off run ahead, go exit run ahead mode. And if in the case we have 93 cycles, then we will have run ahead will have 3 loads, and the number of hits will be different. Okay, so let's go to the second question. Is it possible that every memory access in the program misses in the cache? If so, what are all possible values of X that will make all memory access in the program miss in the cache? If not, why? Show your work. Okay, so let's imagine that the processor, based on the previous one, the processor, as I said, requires at least 31 cycles to prefetch one block, right? So if the processor spends X, if the latency is smaller than 31 cycles, then the processor doesn't have any time to go and prefetch the next load instruction. So imagine that the miss here lasts 31 cycles. Then you enter into run ahead and you are not able to find the next prefetch, the next data block. Okay, so that's one part of the inequality. So imagine that X is now larger than 123. And why am I having the number 123? Because it's like it prefetches, run ahead can prefetch 4 cache blocks. So what is the problem with prefetching 4 cache blocks? So all the prefetched cache blocks, all prefetched cache blocks map to the same cache set. So if they map to the same cache set, so the latest prefetched cache block, the last one, will evict the first prefetched cache block in run ahead. So and this is not the first prefetch, is not the one that triggered run ahead. It's the one that was the first prefetched by run ahead, and because it says that in the beginning of the intro of the exercise in the definitions, so that the cache replacement policy does not evict the cache block that triggered entry into run ahead during run ahead mode. So it will evict the first cache block that was prefetched by run ahead. So what is the problem with that? If we evict the first cache block that was fetched by run ahead, they will have a miss. We will have a miss in the next iteration of run ahead. Which means that we will always miss. That's the problem here. So I want to repeat that. So imagine if we have a miss, we enter into run ahead, and then we prefetch 1 block, 2 blocks, 3 blocks, 4 blocks. So the problem is the following here. So this needs to come into the cache, this miss that was triggered. This, and this were prefetched by run ahead. And they all map to the same set. The problem is that this will evict this. And if we evict this, then when run ahead exits and the program goes to 1, the program will miss because this will not be in the cache. And it will miss all over and over and over again. So that's why it's not working. I think this is the explanation here. So X needs to be smaller than 31 cycles, and X needs to be bigger than 123. So that you miss every time. So what is the minimum number of cache misses that the processor can achieve by executing the above program? Okay, we saw here a case where we were able to prefetch two blocks, two cache blocks. And we saw here that also if we prefetch 4, it is a problem. So we will search what's going on, what's going to happen if we are able to prefetch exactly 3 cache blocks. So to prefetch exactly 3 cache blocks, based on the equations we wrote before, we need to have something between 92 and 124, the latency. Because if we have something below 92, we will prefetch 2. And greater than 124, we will prefetch 4 and we will miss always, as we showed in the previous exercise. So in this case, Runahead will prefetch 3 cache blocks. So if we prefetch 3 cache blocks, then if we have 100 memory accesses, so imagine if for every memory access we go and prefetch 3 cache blocks. This means that for every 4 memory accesses, 3 hit always. And we do not have the issue with trashing, as we explained here. We do not trash because we prefetch 1, 2, 3, and the one that was serviced, which can fit in the 4-way associative cache. So in this case, we have 1/4 of the total memory accesses missing. And 3/4 hitting. 1/4 is 25 cache misses, which is the answer to this question.
Hi everyone, we're going to solve a question on building multi-core processors. So let's get started. You're hired by Amdahl's Nano Devices and to design the newest multi-core processor. GGL, one of AND's largest customers, has found that the following program can predict people's happiness. Okay, let's take a look at the program. So it's a for loop here. Some values read, written to past, same for current, some multiplication happening, and addition, and again the result is written to AI. So A is a large array of 4-byte floating point numbers gathered by GGL over the past years by harvesting people's private messages. Your job is to create a processor that runs this program as fast as possible. Assume the following. You have magically fast DRAM that allows infinitely many cores to access data in parallel. If you relax this strong assumption in parts D, E, and F. Each floating point instruction, addition and multiplication, takes 10 cycles, and each memory read and write takes 10 cycles. No cache is used. Integer operations and branches are fast enough that they can be ignored. Okay, assuming infinitely many cores, what is the maximum steady state speedup you can achieve for this program? Please show all your computations. Okay. So since all these numbers are basically constant across all the iterations, we actually do not need to work with these numbers to solve this question. We actually need to just look at the loop closer in order to basically address this question. So regarding parallelism, so the instructions here in this loop needs to be executed sequentially. So the loop body is basically a sequential part of the execution, whereas consecutive loops can be executed in parallel, or to be more precise, each 12 consecutive loops can be executed in parallel. The reason is that these I minus 12, basically in each iteration, requires an AI in basically 12 iteration before it. Therefore, there is this data dependency between the first and let's say 13th iteration in basically in each group of iterations. Therefore, maximum, we can have 12 iterations running in parallel in order to basically not be stopped by this data dependency. Therefore, the information basically we need is this. The loop body is basically the sequential part of the program. Each 12 consecutive iteration can be executed in parallel. And the reason is because of the data dependency that exists between basically data dependency between the first and 13th, right? Iteration. So, and therefore we need to here use Amdahl's law in order to find out what we can achieve by parallelism. So based on Amdahl's law, the speed up we will have by parallelism would be like this. So imagine 1 is the overall execution time of the program, and then the ratio S between 0 and 1 is the serial part, and here this is the parallel part, right? Parallel part that can be basically parallelized perfectly with n cores. So the execution time would be P over n. And then here we have infinitely many cores. Therefore, this n going to infinity, supposedly this goes to 0, right? So, and here we will have this sequential part, which is basically the loop body in each 12 consecutive iterations. So that will be 1/12 of the execution time is serialized, cannot be parallelized. So we would have here 12 as let's say the perfect speed up that we can have based on the data dependency of this program. So that is the answer for this part. For the second part, what is the minimum number of cores you need to achieve this speed up? Okay, basically, since the maximum speed up here we have is 12, and each 12 consecutive iterations can be executed in parallel and not more. Therefore, here we need 12 cores and not infinitely many. So briefly describe how we would assign work to each core to achieve this speed up. So the goal here is that we need to basically assign consecutive iterations to different cores. So each ith iteration basically needs to go to I mod 12th core. So basically that will be the solution for these parts. Let's go to the next. Okay, let's start here. So it turns out magic DRAM does not exist except in Macondo. As a result, you have to use cheap, slow, low bandwidth DRAM. To compensate for this, you decide to use a private L1 cache for each processor. So here, private L1 cache. The new specifications for the DRAM and L1 cache are: DRAM is shared by all processors. DRAM may only process one request, read or write, at a time. DRAM takes 100 cycles to process any request. DRAM prioritizes accesses of smaller addresses, and write requests assume no virtual memory. The cache is direct map. Each cache block is 16 bytes. It takes 10 cycles to access the cache. Therefore, a cache hit is processed in 10 cycles, and a cache miss is processed in 110 cycles. Why? Because 10 cycles for occurring the cache and 100 cycle to go for DRAM because the data has missed basically in the cache. All other latencies remain the same as specified earlier. Answer parts D, E, F, assuming this new system. Can you still achieve the same steady speed up as before? Circle 1 yes or no, and then please explain. Okay, let's go revisit our loop again. So here in this loop, we have this memory access here. These memory accesses and multiplications in here, right? So this, since these are integers, they're not mentioned or floating point operations. So these, we will basically ignore them here. So one thing which was important from this new part of the question was that we have 16-byte cache blocks. So it means that with each cache block that we bring from memory to cache, we can here access 4 data points because each data point is 4 bytes. Therefore, among these for loop iterations, only 1 per each 4 iteration would basically missing the cache and need to go to the DRAM. And the reason here that I'm not considering 2 separate requests for these ones is that this has been already, as we have discussed, been accessed by a prior iteration. So the data for it in that address would already exist in the cache. So let's take a look at these this loop. So for each 4 iterations, we would have, as we discussed, 1 memory access. So let's assume that we're looking at an iteration without memory access. How long would this for loop take? So that would be 10 cycles to access the cache, 10 here to access the cache, 10 this floating point, 10 this floating point, and 10 to write this one back to the cache. So in the basically iterations that we do not need to go to memory, we would need to access 50 cycles. So let's go back to the solution here. So we first need to write that each 4 iterations, there would be basically 1 DRAM access. And then the total execution time of like serial program would be basically 50 per iteration. So per each 4 iterations here, you would have 100 for the DRAM. And among these 12 iteration batches, we would have here need to multiply for 3. So that would turn out to be 900 cycles. So if we want to have basically same speed up as before, then we need to basically have 12 times the speed up. So each iteration needs to take 75 cycles. That's not going to work because 75 is more than basically 1 DRAM access that basically needs to happen in each 4 iterations, which is 100 cycles. So some iterations, even the 1 DRAM access part of it would be more than the 75 cycles. Therefore, we cannot have same steady speed up as before. No. Okay. The next part is that what is the minimum number of cores your processor needs to provide the maximum speed up. So here for maximum speed up, it's very important for us to minimum number of cores. Yeah. Here for the maximum speed up, it's really important to pay attention to the private data cache locality because since this is like 16. Each block is 16 bytes, and then each 4 consecutive indices would hit in the cache. It is very important that we have basically each 4 iterations here be executed on 1 core. So basically requests from I to I plus 3, here, like this should go here to 1 core. Therefore, among these 12 iterations that we had, and these 4 iterations being divided in each core, overall, we need 3 cores. Okay, so part F, briefly describe how we would assign work to each core to achieve this speed up. So that will
Okay, let's read the question first. An architect is designing a prefetch engine for his machine. He first runs 2 applications A and B on the machine with a stride prefetcher. application A and B both are accessing an array A of 1000 uint 8 element. The only difference between application A and B is while the array indices of application A is incremented by 4, the array indices of application B is multiplied by 4. We know that I and sum are in registers while the array A is in memory. We also know that a cache block is of 4 byte in size. The first question is, what is the prefetch accuracy and coverage for application A and B respectively using a stride prefetcher? Now, to understand the coverage and accuracy of a stride prefetcher in application A and B, let's first try to understand how many memory accesses application A would generate. Application A would access elements A0, A4, A8, A12, and so on. So this means in total, application A would create 1000 divided by 4, that's 250 memory requests. Out of these 250 memory accesses, the first two accesses, which is going to A0 and A4, won't be predicted by the prefetcher because the prefetcher would understand this is the first stride of 4 cache line. Then, once it learns the stride, it can prefetch cache line A8, A12, and so on. In fact, the prefetcher would prefetch the cache line A1000 also, which won't be required by the program. So in total, the prefetcher would generate 249 prefetches. As per the formula, we know the accuracy of a prefetcher is number of prefetch which is used by the program divided by the total number of prefetch. As per this rule, the accuracy of prefetcher A, the accuracy of stride prefetcher in this program A would be 248 out of 249 because the last prefetch, which is going to add in element 8000, won't be used at all. Similarly, the coverage of the program, the coverage of the prefetcher is defined as the total number of memory accesses which is predicted by the prefetcher divided by the total number of memory accesses, right? As per this definition, the total number of memory accesses would be 250, out of which 248 would be successfully predicted by the prefetcher. Hence, the coverage of stride prefetcher in application A would be 248 upon 250. Now let's see what would be the stride prefetcher's accuracy and coverage would be for application B. As we can see, application B will access the array element A1, A4, A16, A64, and A256 only. So that means in total, the program would make only 5 memory accesses. But in this case, there won't be a constant stride between these accesses. And as a result, the stride prefetcher cannot prefetch any of the cache line, and the prefetch accuracy as well as coverage both will be 0 for application B. Now let's go to the next question. Suggest a prefetcher that would provide better accuracy and coverage for application A. Now recall that for application A, the stride prefetcher fails to prefetch memory accesses which is going to element A0 and A4 because these are the first two accesses which is giving us the stride learning. But a next block prefetcher would always prefetch the next cache block without even looking for a constant stride. Hence, in this application A, a next block prefetcher would actually successfully prefetch 249 out of 250 memory accesses, whereas 249 out of 250 prefetches would be correct. So in this case, the prefetcher's accuracy would be 249 upon 250 and prefetcher's coverage would be 249 by 250 again. So a next line prefetcher would work better than stride prefetcher for application A. Now let's suggest a prefetcher that would provide better accuracy and coverage for application B. Most common prefetchers such as stride, stream, next block prefetcher would not improve prefetch accuracy for application B, as application B does not have an access pattern for which prefetchers are commonly designed. So in this case, some form of pre-execution based prefetcher like Runahead execution could help improving prefetch accuracy. Now let's go to the next question. Would you suggest using Runahead execution for application A? If yes, then why? If no, then why not? As we know, Runahead execution could still provide good prefetch accuracy even for application A, which has regular access pattern. But in Runahead execution, it might not be possible to prefetch all cache blocks before they are accessed, as Runahead execution happens only when the application is stalled on a cache miss. So in this case, for application A, a stride prefetcher or an H block prefetcher could possibly prefetch all cache blocks before they are accessed, as prefetching happen in parallel with the application's execution. So for application A, Runahead execution will not be suitable. But in the case of application B, whose access pattern does not have a regular stride, commonly used prefetchers are not designed to prefetch an access pattern like this. So in this case, Runahead execution can potentially prefetch some of the cache block. And this is especially true as the address of the cache block in application B does not depend on the data from a pending cache miss. So for application B, we would still suggest going for Runahead.
Okay, hello everyone. So now I will try to discuss one of the questions that we cover in homework number 3, and the question is basically about genome analysis. The number for the question is 3 as well. So the question states that during a process called read mapping in genome analysis, each read, which is basically a subsequence of our DNA, the entire DNA. So think about the read is just genomic subsequence. And this read is mapped to one or more location in the reference genome based on the similarity between the read and the reference genome segment at that location. So basically, we try to infer the potential location of this extracted read in a comparison to the entire reference genome or the reference sequence. So there are basically many potential mapping locations, and these locations are identified based on the presence of exact short segments, and these short segments we call them k-mers, and k here is a parameter which is the length of such short segment. So if it is 4, then we replace the k with 4, for example. So these short segments, we extract them from the read sequence, and if they exist in the reference genome, then we have some insight about these potential locations. The locations of the k-mers in the reference genomes are usually determined using a hash table. So a hash table here will be used as one type of the index data structure. There are other alternatives, but in this question, we will be using a hash table. So each entry of the hash table stores a key and a value. So we have key-value pair stored in the hash table, where the key is the k-mer itself, which is the content, or the ACGT letters that are extracted from genomic sequence. And the value is the list of locations at which the k-mer occurs in the reference genome. So I hope this is clear until now. And the challenge in designing such a hash table is deciding which k-mer or which k-mers to use as keys, as it affects the size of the hash table and the number of potential mapping locations, which affect the execution time of read mapping. So basically, if we have more k-mers stored in the hash table, then we will spend more time if we have more location stored in the hash table for each k-mer, then we have more work to do, basically. So in this question, you will be exploring the trade-offs between two strategies of k-mer selection. And since these k-mer are very short compared to the entire read sequence, so think about k equal 4 and a read sequence equal 100, for example, then there are many ways that you can extract such k-mers, very short k-mers, from the read sequence. And in this question, we discuss only two strategies or two methods to extract k-mers. The first one, we refer to it as non-overlapping formers, and 4 here is the k, which is the length of the short segment extracted from the read or the reference. So every non-overlapping formers in the reference genome is used as a key in the hash table. So as we mentioned, that we always store key value pair in the hash table, and the key here will be the formers and the value will be the location. For example, here we are giving you an example such that it's clear. This is the reference genome, and this example contains only 2 non-overlapping formers. Why is that? Because if you check here how many characters we have 8 characters. So if we extract only the non-overlapping k-mers, then we have this first k-mer and this the second k-mer, which each of them is of length 4 characters. And these 2 k-mers, the extracted one, and the hash table would have the following entries: the first k-mer extracted and its start location. So the first character start at index 1, assuming that we index or we have this character starting from 1, not 0. And the second k-mer, which is the other non-overlapping formers, start at location 5, which is this character. Now what we store in the hash table, basically, this key value pair and the other key value pair. So I hope it's clear for the first method. Now the second method, we call it non-overlapping formers minimizers. So these the same method we use here, but we try to minimize the number of seed we extract. Now I'll explain in more detail about it. So for every non-overlapping former in the reference genome, the lexicographically minimum former of it and the 2 subsequent non-overlapping formers is used as a key in the hash table. So every time we need to extract 1 k-mer and another 2 subsequent non-overlapping formers. So we extract 3 seeds or 3 k-mers from a sequence, and then we try to calculate the lexicographically minimum k-mer out of these 3 k-mers. And here's an example. So the segment, which is this one, contains only 2 non-overlapping former minimizers. These are the minimizers extracted from this long or relatively long sequence. Now, how we calculate them? So basically, we try to extract all non-overlapping k-mers. So the first k-mer is the 4 A's. Why is that? Because k is 4 here, and this is the first 4 character. Now, what is the second non-overlapping k-mer? Is these 4 characters, which is TTCA. And the third k-mer that is also non-overlapping, this is very important, which is ACGG. So now we already extract 3 k-mers out of this sequence. Now in minimizers, we need to sort them, and then we pick only the lexicographically minimum out of these 3 seeds. Now, what is the lexicographically minimum? Apparently, when we compare this to this, then the first one is minimum. When we compare the first to the third, then the first character and both of them are equal. Then we go to the second character. Here is A, and here is C. So A is before actually C in the alphabetical order. So if the 4 A's is basically the one we consider as a minimizer. We repeat the same thing, but now when we extract the next 3 k-mers, the first one will be this k-mer. So TTCA is the first k-mer in the next iteration. And ACGG is the second k-mer, and GCAG is the third k-mer. Now we sort them, and then we try to pick the minimum as a minimizer, which is the ACGG. Okay, I hope this is clear. I think, yeah, the rest is what I exactly explained. So now we can move to and this is exactly what we store in the hash table, which are the k-mer itself and the start location of each k-mer. Here's 9 and here's 1. All right? Okay, so now let's move to the question. And I really recommend all of you to go and watch my lecture again, especially starting from slide 60, where I explain about read mapping process, and it will help you a lot in solving this question. And this lecture is lecture number 8 in the computer architecture course for the fall 2020 semester. All right, so here I copied again the 2 methods just as a reference while we are solving the question. Okay, so now the first point in the question. Suppose that you would like to map a set of reads to the following reference genome. So here's the reference genome. So this is the reference genome. And note that we already separated by underscore such that you already know where are the k-mers, so such that we save your time and you don't make mistake while you count every 4 characters. So answer the following question based on the information given above. Please list all key value entries in the hash table if we use all non-overlapping formers, which is the first method we discussed, as keys. The order of the entries is not important. Okay, so the first method is simply just extract every 4 characters that are non-overlapping and store them in the key column of the hash table, and then extract the start location of every k-mer and store it in the hash table in the second column. So now I just indicate here the start location of each k-mer just to make our solution easier. And now, okay, if you want to extract the first k-mer, we already split them using the underscore sign. So the first one will be this k-mer as it is. So we are going to store A, which are the 4 characters, and this k-mer is located at location 1. Now the second k-mer will be the second subsequence here, which is A, T, A, C. Now this k-mer is located where? Now, since I add this 5 here, so we already know the start location. For you just need to count the number of characters and define the start location of such k-mer. So the first location is 5. Now, do we have this k-mer anywhere in the reference genome as or can we extract such k-mer from another location? So we check this k-mer, no, doesn't match, no, it's not the same. So we have here a head. So this k-mer is exactly the same as we extracted from there. Then we don't need to store it in a separate entry because it already matched there. So what we need to do is just add a new location next to 5, which is 17. Now we do the same thing. We iterate over all k-mers, all possible k-mers using this method as the question specifies. And we see here there's a head, and this one is starting at location 41. Do we have other heads? I guess no. And we keep doing the same thing. The third k-mer will be this. So we record it here as a key, TGAT, and then we check, do we have TGAT somewhere? I think no. Then we only record that location, which is 9. We keep doing the same thing until we extract the entire hash table, and this is what we will get. So I hope it's very much clear. I think it's straightforward. All right. So now let's go to the second part of the question, which is B. Please list all key value entries in the hash table if we use all non-overlapping former minimizers as keys. Please list all the entries of this hash table. The order of the entries is not important. Okay, so now we want to apply the second method, which is the minimizers method. Okay, so we will use the same reference genome for the reference sequence here, and we already have the start location indicated. So what we need to do, we need, following the method we described, we need to extract every 3 k-mers that are non-overlapping, and then sort them and pick the lexicographically minimum k-mer and store it in the hash table. So where are the first 3 k-mers? These are the 3 formers that are non-overlapping. Okay, now remember that A is less than C, less than G, and G less than T in the alphabetic order. So what is the minimizers out of these 3 k-mers is basically 4 A's, right? So we store them here, 4 A's. And we store also the location of 1. Now we cannot search if these 4 characters exist anywhere else, and then we append the start location in the hash table. Why is that? Because we need to check only every 3 k-mers and pick the minimum, and then we check if we have other minimizer exist or not. So what we need to do is that we proceed to the next 3 k-mers that are these, and then we check the minimum. So all of them, the first one starts with A, the other starts with T, the third starts with C. So the minimum should be the one starting with A. And then we need to store A, T, A, C. Again, we cannot search for ATAC if it exists somewhere else, like here, and then append here 41. No, it won't work this way because we need only to store minimizers. So don't hurry, wait until you finish all k-mers. And here the location is 5. Now, what are the next 3 k-mers? So we will take starting from the 3rd, 4th, and 5th k-mer, which are these. Now the first one starts with T, the second one starts with C, the third one starts with A. So basically the minimizer will be the third one. So do we have it already stored? Yes, it's here. So we need to append here 17 next to it. Now we proceed to the next iteration where we start from here all the way to here. So the first one, which is this guy, starts with C, the second one starts with A, and the third one starts with G. So do we have, so what is the minimizers? Is basically this one. So do we have it stored? Yes. So do we need to store it again? Doesn't make sense. Then we skip it. Now, where's the next iteration? Starting from 17 all the way to here. So we have the first k-mer start with A, second k-mer start with G, third k-mer start with T. So where's the minimizer? Is the one start with A because it's lexicographically minimum. But it's already stored. So we cannot do anything here than just skip this window because it will be duplicate. And then we start from this k-mer all the way to this k-mer. Now we have the first k-mer start with G, the second one starts with T, the third one starts with G. So which one is a minimum? So the lexicographically minimum would be the one starts with G, but we have two of them. Which one to pick? So we look to the second character. Both of them are T, then we cannot decide. We look into third character. Both of them T, we cannot decide. And then we go to the fourth character. The first one ends with G, but the other one ends with T. So which one is minimum? The one ends with G. So we store this one as a minimizer, which is G, T, T, G. So this will be our key, and the location will be 21. I hope it's clear. I think we covered most of the cases until now, so I think I don't need to continue, but feel free to ask any question over email or over Moodle or Piazza. Yeah, we can discuss in more detail over there. All right, and what you will get at the end is this table. So I think we already found the one located at 1, at 5, and 17, and 21. So the remaining, when you try to continue solve it by yourself, you should get the one located at 33 and 41. And this will be the answer for point B. Okay, so now we can proceed to point C. So in C, assume that we calculate the size of the hash table allocated in memory as this equation, and this equation gives you the memory footprint in bytes, where E is the total number of hash table entries and P is the total number of locations stored across all values, which is the second column basically in the hash table. Now we want to calculate the memory footprint in bytes of each of the two hash tables you design in A and B, and you need to show your work. Okay, so this is for your reference. These are the two hash tables that we already generate for A and B. Okay, and we have an equation. We have an equation that is given as this, as following, and what this equation requires as an input parameter, E and P. What is E? E is the total number of hash table entries. For example, the first hash table here, how many entries, which are the number of rows. So how many of them we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So for A, to calculate the memory footprint for the first method, which is A here, we need to substitute E with 8 and P with the number of locations stored in the second column here. How many locations do we have? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have here 13, and we have here 8 entries. So calculating the equation with these two parameters will give you the memory footprints in bytes for the first one, which is 21 bytes. So directly applying just the values. Now for the second method, which is the minimizers, how many entries do we have? We have 4, which are these. And how many locations do we have? 1, 2, 3, 4, 5, 6, 6 locations. So E will be 4 and P will be 6. So applying that directly in the equation will give you that the memory footprint of the minimizer method is only 10 bytes. Now, comparing this memory footprint to that, apparently the minimizer method provides the least memory footprint. And that's why we call it a minimizer, because it minimizes the number of k-mers that we store in the hash table. So out of every 3 k-mers, we store only a single k-mer as a minimizer in the hash table. Now that can tell you more about the speed up that you can have when you query the hash table, because apparently you will have less k-mers, and these k-mers represent less potential location in the reference genome, then that will lead to have a faster pipeline or faster read mapping process, as we will see next. Okay, there are more details in the solution. I recommend you to read it and try to understand it. Let me know if you don't get any of these details. Okay, now let's go to the fourth point, and it's the last point in this question. Here, we assume we can query the hash table in this much number of cycles, where E is the total number of entries in the hash table. Okay, and now a read mapper queries the hash table using the first former of the read. So assume that we already calculate the hash table using the solution for point A and B. Now we would like to query this hash table. This is the first and this is the second, using only the first 4 characters of the read. So we extract the first 4 characters from the read sequence and try to query this hash table and see if they exist or not. Okay, and we calculate then the edit distance between the read and the reference genome at each location returned by the hash table. So this is very important. So at every location returned by the hash table as a response to our query, we need to perform edit distance operation. So if the hash table returns 4 locations as a head, then we need to perform edit distance 4 times at every potential location or stored location. Now, calculating the edit distance itself takes L square cycles, where L is the length of the read sequence. If the edit distance between the read and the segment in the reference is higher than a certain threshold that's given by the user, then the read mapper discards the location, and you can guess why. So basically, we compare the read to a portion of the reference genome, and then if the number of differences between them exceed a threshold, then they are insignificant, or the matches between them are less than expected, so they are not interesting to us. So we just discard them because they are highly dissimilar. Now we refer to the cycles spent in calculating the edit distance for segments at discarded location as wasted cycle, and the name says it all. So we already waste some time do calculation, but then we discover that these 2 sequences are really dissimilar. Now, when we profile read mapping with non-overlapping formers and non-overlapping former minimizer strategy, we find that wasted cycles over total cycles ratios to be 0.9 and 0.8 respectively. Assume that we want to align the read, which is this one, to the reference genome above, which is given around point A in the previous points we were discussed. The question asks you to find the wasted cycles when aligning the read using the first method and the second method strategies. And you need to show your work. So it's important to not provide only the final answer. Okay, so in short, whenever you perform read mapping, the number of cycles are as follows. So the first thing, you have a read sequence, you extract the first 4 characters, you send them to the hash table and try to query them. Now, querying the hash table itself will require log or base 2 log E. This is only for querying the hash table. Now, the hash table assumed returns some numbers of location, let's assume to be n. This number of location, at every location of this returned location, we need to perform edit distance operation. So this n is multiplied by the number of cycles for performing edit distance, which is given the question as L to the power 2. So this is the time. This is the number of cycles required to query the hash table, and these are the number of cycles to perform edit distance calculation. Okay, I think it's straightforward in this question. What you need to do is just extract the first 4 characters from here, which are G, T, T, G, and try to query the hash table. Now let's see, do we have GTTG here? No, 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 we have it here. So we got a head here. And this head will lead to having 2 locations as n. So using the first hash table or the first method to extract k-mers, which is non-overlapping formers, leads to have, to have n as 2. And E here is the number of entries in the hash table, which is 1, 2, 3, 4, 5, 6, 7, 8. So we have base 2 log base 2 log to 8 plus 2 times L square, and L is the length of the read sequence. So what is L here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's 12 times 2. Now this is not the answer, because the question is not asking for the number of cycles, but rather it's asking for the number of wasted cycles. And this equation will give you the total number of cycles to perform read mapping for this read. This will give you a number. And now, based on this equation, which is wasted number of cycles over total cycles, we can calculate the wasted cycle. So the wasted cycle, W, wasted cycle is equal total cycle times, so the first method is 0.9 times 0.9. Now we already calculate the TC here, which is the number given by this equation, so it's easy to calculate the wasted cycle. Now we do the same thing with the second method. So the number of entries in the hash table here is 4. So we substitute here as 4, right? Now, let's look for the same k-mer we extract from the read, which is GTTG. Do we have GTTG here? No, no, we have it here. Okay, so how many locations do we have? Only single location. So we are going to perform at a distance only once. And n here will be 1, not 2. And L should remain the same because we are using the same read. So it's directly, we can apply this equation, and then we could calculate the WC, or the wasted cycles, using this equation, but the 0.9 here would be 0.8 as given by the question. You can see it here. I hope this is very much clear. Yeah, so now let's see the answer maybe. So this is the answer for the first part, where the wasted number of cycles is 261.9. And for the second equation, or the second method, is 116.8. Now you can see that using the minimizer method, we have less number of wasted cycles. That is mean we have more efficient or more time efficient process with the minimizer, because apparently you can see here the hash table is basically less. So we have less number of entries in the hash table and less number of locations. So whenever we query a seed, we probably get less work to do and less number of edit distance operation. So maybe you can see here the number of location, the maximum number of location we have in the first hash table is 3, which is the second entry. Same thing in the second hash table, but normally in other cases you might get different numbers, and probably the minimizer will remain the best. Okay, so this is all for this question. I hope I was clear enough to clarify, and I will be happy to take any question again over email, Piazza, or Moodle. Thank you so much, and wish you all the best in your exam.
We have a memory consistency question. In this question, a programmer writes these two pieces of code to run simultaneously in different threads in different cores on a processor called SC that implements sequential consistency. So we know that X and flag are allocated in the main memory, while the values of A, B, and C here are stored in some private registers. So we know that the initial values of all memory locations and variables are 1. And we assume each line of the C code is a single instruction. So let's look at the questions. The first question, do you find something that could be wrong in the C code segment? What can be wrong in the C code segment? Let's look at that. So if you notice, there's a loop here, and it iterates as long as flag 0 equals to 1. So from the assumptions, we know that flag 0 equals to 1 in the initialization, and its value never changes. So the problem is thread 1 will never finish. In the second part of the question, we are asked to find all possible values that X0 can get after executing these codes. So from the first question, we know that T1 never finishes because there is an infinite loop there. So let's look at which instructions can actually change X0's value. So we have instruction T00, instruction T10, and instruction T11 that can change X0's value. And we have another instruction here, but the program never reaches here because of the infinite loop. These instructions can execute in different orders. Sequential consistency guarantees that T11 will be executed after T10. So the all possible orderings are just 3 of them. T00, T10, T11. This is one. Another one is T10, T11, T00, and another one is T10, T00, and T11. So for all these ordering of these instructions, let's look at what value X0 gets. Here T00 is, so here X0 is 2, and then in 10 it becomes 1, and then we increment it by 2, so it becomes 3. And here we start with x equals to 1, and then in T11 it increments to 3, and then in the last one we just assign the constant 2. And then let's look at this one. It starts with 1, and then it's assigned to 2, and then it increases by 2, so it becomes 4. So these are all 3 possible values that X0 can get after executing these 2 threads. Let's go to the next question. So the next question asks about all possible values that A can get in this processor after running the C codes. So let's look at A. A's value changes in T0.2 or T1.3. And we know from the first question that the code never reaches to T1.3 because of the infinite loop. And if we consider T0.2, so the A's value is double of X0, right? So we should consider all cases that T0.2 can get in this order of codes that we looked at in second part of the question. So here T0.2 has to come after T00. Therefore, T0.2 can get into here, 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 and here. So we can calculate all values based on this. So if it's here, A equals to 4. If it's here, A equals to 2. If it's here, A equals to 6. And here, 4. Here, 4. And here, 8. Therefore, all possible values that A can get are 2, 4, 6, and 8. So the next part of the question asks about all possible values that B can get. B is set only in this instruction, and it's purely depending on Y0's value. So we need to check what values that Y0 can get and what can be the ordering of these instructions. So you can see that Y0 only changes at this instruction, which can never be reached because of the infinite loop again. And we know from the assumption that Y0's initial value is 1. Therefore, B only can get one value, which is 0. In case of no memory consistency, core A can see core B's memory requests executed in different orders, rather than all of them in the order specified by the program. So in this case, we also need to look at other permutations that we didn't consider in the second part of the question. So here, let's look at the instructions that can change the value of X0. Again, this one, and this one. So earlier we made the assumption that T11 always executes after T10. But we can also see from perspective of core 0, we can observe that T11 executes first and then T10 executes. So in second part of the question, there were these 3 possible ordering of these instructions. And now we need to also consider the cases where T11 executes before T10. Therefore, it implies this T11, T10, T00, T00, T11, T10, T11, T00, T10. And let's calculate what X0 gets in these three combinations. So the first sequence ends with T00, which makes X0 equals to 2. So this result is 2. And here it ends with 10, meaning that X0 can get the value of 1. And this ends with T10, meaning that it can get the value of 1 at the end. Therefore, all possible values that X0 can get in this question are 1, 2, 3, and 4.